Magnus Effect. Magnus Effect. Magnus Effect is a phenomenon. Magnus Effect is a phenomenon in which a spinning object or body, moving through a fluid departs from its actual trajectory if it were not spinning from its actual trajectory if it were not spinning because of pressure difference that develop in the fluid, and that fluid should be non-viscous because of pressure difference that develop in the fluid as a result of velocity changes induced by the spinning body or object. The Magnus effect is a particular manifestation of Bernoulli's theorem, and it will be realized in the video coming next. A video will be coming, and the Magnus effect will be realized by viewing this video, in which Roberto Carlos, eminent footballer, kicked a free kick against France. Let's have a look into the video.
Careful look about it. It's placed absolutely perfect. Look at that. I mean, everything's set that he's going to hit it. I just wonder if they're kidding us on.
It's what, all of 30 yards.
Having a good careful look about it. It's placed absolutely perfect. Look at that. I mean, everything's set that he's going to hit it. I just wonder if they're kidding us on.
It's what, all of 30 yards, Andy?
Well, why not? It's a 30-yard free kick with a 20-yard run-up.
Dear, I don't believe it. What a goal we have just seen from Roberto Carlos. That is amazing.
Well, that was what was missing in Euro 96. That is quite incredible. Not so sure about the goalkeeper's position and what he saw, but we can't deny the quality of the strike. It had power, it had bend, it had accuracy. Watch this. Starts way wide of the goal. That's 2-3 yards wide and just clips the inside of the post. That is quite a magnificent free kick. I'm not so sure we'll see one better than that for many a year. Quite exquisite.
An absolutely stunning shot. Barthez, well, he was as much a spectator as I was.
Here, the Brazilian Roberto Carlos kicked the ball tangentially, and initially the ball was traveling along the original trajectory, and it departs from its original trajectory due to difference in pressure acting on the two sides of the football. Here the ball departs from its actual trajectory, and this deviation of path of the ball is called Magnus effect, and we can explain this phenomenon in this way. This is the football, and it was striked tangentially, and the football rotates or spins about its own axis anti-clockwise. The ball spins anti-clockwise. In the diagram, the ball spins anti-clockwise, and air is flowing in the opposite direction. The football were trying to travel in forward direction, and air is flowing in the backward direction. This is the direction of airflow. Air is flowing and touching the two sides of the football in this way. This is the direction of airflow. The direction of airflow. And the football spins about its own vertical axis anti-clockwise in horizontal plane. The football kicked by the footballer The football kicked by the footballer tangentially. The football kicked by the footballer tangentially spins anti-clockwise about its own axis. Anti-clockwise about its own axis. About its own axis. V1 is the velocity of airflow on the right hand side of the football, and V2 is the velocity with which air is flowing in the backward direction, and we can denote the pressure P1 which is acting on the football or ball on the right hand side of the ball, and P2 is the pressure which is acting towards right on the left hand side of the football. As V1 is less than V2, P1 will be greater than P2, and a pressure difference P1 minus P2 will be acting towards left, and a force F which is the product of pressure difference and area of cross section, that is P1 minus P2 into A is the force which acts towards left and which is known as Magnus force. Magnus force, and Magnus force acts horizontally towards left, and actual direction is in the forward direction, and resultant motion of the ball will occur along this curved path. So here this is the curved path followed by the ball in the air. That means the ball or football departs from its actual trajectory and travels along the curved path under the action of the Magnus force. This spinning ball drags some of the air. So first of all, the football kicked by the footballer tangentially spins anti-clockwise about its own axis, and the spinning ball drags some of the air around it. The spinning ball drags some of the air around it. The air which is flowing in the opposite direction. It should be is flowing. The air which is flowing in the opposite direction of the spin of the ball gets retarded. Here we can denote the air flow on the right side of the football, and this air gets retarded because air is flowing in the opposite direction of the spin, whereas the air which is flowing in the opposite direction of the spin of the ball gets retarded, whereas the air flowing on the other side of the ball will be accelerated as this airflow occurs in the same direction of spin of the ball. In the diagram here, air is flowing in the backward direction and in the same direction of the spin of the football. And in this case, this air gets accelerated. In this case, V1 is less than V2. That means the velocity of airflow on the right side of the ball will be less than the velocity of airflow on the left hand side of the ball. Hence, greater pressure acting on the right side of the ball, that means greater pressure P1 acts on the side of the ball where the airflow is slowed down, as air is flowing in the opposite direction of spin of the body with a velocity V1. Greater pressure P1 acts on the side of the ball where the airflow is slowed down with a velocity V1. We can draw the diagram again. This is the actual trajectory or straight line path along which the football was trying to travel in air or fluid, and the football spins about its own axis in horizontal plane anti-clockwise in this direction. Air is flowing in the backward direction. In this direction. If we denote a point, this is what the air is flowing, and this airflow is slowed down because air is flowing in the opposite direction of spin of the body or ball, and the velocity with which air is flowing on the right side of the ball is v1. Similarly, air is flowing on the other side of the ball in this direction, and we can denote the velocity of air flow at this point. This is the velocity. v2 is the velocity with which air is flowing. Air is flowing on the left side of the ball, and in this case this air flow is accelerated because air is flowing in the same direction of spin. Airflow is accelerated. Greater pressure P1. A greater pressure P1 acts towards left on the right side of the ball, and smaller pressure, lesser pressure P2 acts towards right on the left side of the ball. So here greater pressure P1 acts on the side of the ball where air flow is slowed down with velocity V1, and a lower pressure P2 acts on the other side of the ball. Lower pressure P2 acts on the other side of the ball where airflow where airflow where the air is flowing with a velocity v2, with a greater velocity v2. According to Bernoulli's theorem, P1 plus 1 by 2 rho v1 square equal P2 plus 1 by 2 rho v2 square, where rho is the density of air, or comma P1 minus P2 equal 1 by rho v2 square minus v1 square. P1 minus P2 equal 1 by rho v2 square minus v1 square. As v2 greater than v1, that is the air on the left side of the ball, the air flowing on the left side of the ball, the air flow on the left side of the ball tangentially moves with greater speed v2, moves with a greater velocity v2 than the velocity. The air flowing on the left side of the ball moves with greater velocity v2 than the velocity v1 of air flow touching right side of the ball, comma. That means as v2 greater than v1, so we can say that p1 will be greater than p2. So here v2 is greater than v1. That means v2 square is greater than v1 square. That's why p1 will be greater than p2. P1 greater than p2. Here a pressure difference P1 minus P2 acts towards left, and P1 minus P2 into area of cross section A is the Magnus force. The pressure difference P1 minus P2, and so also a force F equal P1 minus P2 into A, where A is the area of cross section of the football or ball, which is known as Magnus force. In this case, the first letter of Magnus should be written in capital M. We can denote the forward direction or original actual trajectory of the ball. This is the trajectory along which the ball will be moving if the ball does not spin. This is the actual trajectory or actual direction of motion of the body if the ball were not spinning. And Magnus force acts towards left in this direction. Magnus force, that is P1 minus P2 into A, which is the Magnus force, acts towards left. This is the Magnus force acts towards left on the ball due to difference in pressure, because air flowing on the two sides of the ball will be moving with different velocities, and the football or ball will follow this curve path. That means the football departs from its actual trajectory under the action of Magnus force. This is the curved path. This is the curved path followed by the ball or football, followed by the ball or body in moving in the fluid. This is the curved path or resultant path along which the ball or football will be moving. Football or body. Here the football or body departs from its actual trajectory due to difference in pressure or pressure difference acting on the two sides of the football, as different layers of air are flowing on the two sides of the football with different velocities. Under the combined action of Magnus force, F equal P1 minus P2 into A, towards left, under the combined action of Magnus force towards left of the ball and tendency to maintain its original motion or original trajectory without spinning along the original trajectory, the ball will move along the curved path. That is the ball or body departs from its actual trajectory. In the diagram, Roberto Carlos, legend Brazilian footballer, strikes the football tangentially. So this is the football to which he strikes the ball tangentially, and he applies a force tangentially on the football. A tangential force is acting, and we can denote the actual trajectory. Along this direction, the football was traveling. And the ball spins anti-clockwise due to application of tangential force. The football spins about its own axis anti-clockwise direction, and air is flowing in the backward direction. As shown in the figure, and a pressure difference P1 minus P2 will be acting towards left due to different velocities of airflow in the backward direction. V1 and V2 are the velocity of airflow on the two sides of the football. So here V2 is greater than V1, and two pressures are P1 and P2. P1 will be greater than P2. Pressure acting on the right side of the ball will be greater. The pressure difference P1 minus P2 will be acting towards left on the ball. And the football follow this curved path, and it departs from its actual trajectory. This is the direction of resultant motion when the football spins, and this is the actual trajectory. It will follow if the football does not spin. But if it spins about its own axis in anti-clockwise direction, then it will follow that type of curved trajectory. This curved path is the resultant motion of the football, and this deviation of motion due to pressure difference on the two sides of the body or football is known as Magnus Effect. German physicist Heinrich Gustav Magnus described the effect in the year 1852. The curved path followed by the football, known as the banana kick, is largely due to The ball spinning is largely due to the ball spinning motion about its vertical axis and the Magnus effect causing horizontal force. The Magnus effect causing a horizontal force that moves the ball from straight line in its trajectory. That moves the ball from its straight line in its trajectory. So this is the original trajectory, and towards left, Magnus force F acts, and this straight line is the original trajectory. The ball spins anti-clockwise, and the ball travels along this curved path, and this is the resultant curved path of the ball due to Magnus effect. We can mention another application of this effect effect in table tennis. The Magnus effect is easily observed. In table tennis, Magnus effect is easily observed because of the small mass and low density of the ball. In table tennis, Magnus effect is easily observed because of the small mass and low density of the ball. In baseball, pitchers often import different spins on the ball. Pitchers often import different spins on the ball, causing it to curve in the desired direction due to Magnus effect. But the Magnus effect is not responsible for the movement of cricket ball seen in the conventional swing. For the movement of cricket ball seen in the conventional swing bowling, although it may be responsible for Malinga swing. It may be responsible for Malinga swing. The first scientific investigation to find out the reasons of cricket ball swing was carried out by the scientist Cook, where he tried to explain this with the help of boundary layer theory. The scientist Cook tried to explain this effect with the help of boundary layer theories. In the diagram, we have Anton's Flettner's rotor aircraft. Some aircraft have been built that use the Magnus effect to create lift with a rotating cylinder. Magnus effect to create lift with a rotating cylinder at the front of a wing, allowing a flight at lower horizontal speeds. Also, external ballistics. We can explain what is external ballistics. The Magnus effect can also be found. In advanced external ballistics. Magnus effect can also be found in advanced external ballistics. We can denote the direction of Magnus force acting on the bullet fired. This is the direction in which Magnus force acting on the bullet. A spinning bullet in flight is often subjected to a crosswind. Blowing either the left or right. Also, the bullet experiences small sideways wind. Due to yawing motion. It causes a Magnus force to act on the bullet. It causes a Magnus force to act on the bullet. To act on the bullet, and there will be deflection of the bullet. There will be deflection of the bullet's flight path.